Alright, in this video I'm going to show how to not only use the confidence interval for the mean, but also to try to understand how it really works and why it works. And so the question we're going to answer to help us understand this is, what is the average height of girls at our high school? Well, obviously we have a lot of people in our high school. At our high school we have, I don't know, around 500 kids, so probably somewhere around 250 girls. Don't really want to take the time, energy, money spent to maybe hire someone to measure everybody or go around and measure everybody. So what we're going to do is think about a sample of 30 girls. So n is going to be 30 girls, n is our sample size. Let's go ahead and assume that our x bar, our sample average, the average height of those 30 girls is 64 inches, and our standard deviation of our sample would be 2 inches. So, I just made that data up. I didn't actually go out and measure those people, but for the purposes of understanding the formula, this is going to work well. The formula is up here. You can see that x bar is your sample mean, so it's going to be 64. Z sub alpha over 2. Remember that alpha is the area in the tails of a normal curve. Alpha divided by 2 is the area in just one tail. So this just means the z-score at those points. The z-score can be calculated by looking up on a table. For this instant, we're going to be talking about we're going to do a 95% confidence interval. For a 95% confidence interval, you want to go out 1.96 standard errors, and you can look that up in a z-chart or off a table. So our z-score for a 95% confidence interval will be 1.96. Our standard deviation is 2 inches, and we don't actually know the standard deviation of the population because we didn't actually measure everybody in our population. Our population would be all the high school girls. So when n is 30 or more, you can replace the population standard deviation with the sample standard deviation. So 2 inches divided by the square root of 30. And then you'll notice you do that exact same thing on the right side, but instead of a minus, you use a plus. So why do you do this? That's the question. So I'm going to try to explain that. Well, if we went out and found 30 girls at our school and averaged their heights, we would come up with a number. In this case, I'm saying we came up with 64 inches. Well, let's say this dot represents the average of those 30 girls. If I pick a different 30 girls, I will probably get a different average. Maybe I'll get something a little over 64. If I go out and pick another 30 girls, I'll get a different number. So you end up with this distribution where this end down here might represent, I might happen to pick 30 girls that are relatively short and get a very low average. Each dot, again, represents the average of 30 girls' heights. Or I might randomly happen to pick 30 girls that happen to be above average in height, and I might end up with an average up here. But most of the time, I'm going to get x bars, sample means, that are somewhere in the middle. Okay? So, in this case, I'm saying we came up with an average height of 64 inches. So if I had to make a point estimate, if I had to come up with one answer of how tall I think what I think the average height of all the girls in our high school is, which by the way would be represented by the Greek letter mu, the population mean, I would guess that it's 64 inches. The sample mean is our best estimate for our population mean. But sometimes it's not good just to give one point estimate. It's better to give an interval estimate, or what we call a confidence interval. So that's what we're doing here. So these numbers down along this horizontal axis actually represent the average of 30 girls. We know the standard deviation, if each dot represented one single girl's height, the standard deviation would be 2 inches. But we know from the central limit theorem and our previous study that each dot represents the average of 30 girls, that we have something called the standard error of the mean. This is the symbol, means the standard deviation of the sample means, and it's found by taking the original population standard deviation divided by the square root of n. So I've marked off some lines here. We know that most of our data will fall within 3 standard errors of the mean. Okay, so this is one standard error. So to figure out how spread out this distribution is, I need to take 2 divided by the square root of 30 here. So if I take 2 divided by the square root of 30, that's going to tell me how much each standard error is up here on the graph. And you can see that's happening right here. in our formula. Oh, by the way, I wanted to show you that I rewrote this formula in this form. Okay? Notice that the left side and the right side are identical except for the plus or minus. So another way to write this formula would be to say we're going to take x bar, we're going to add our z-score times our standard error of the mean, then we're going to subtract our z-score times our standard error of the mean. So the z-score tells you how many standard errors you are from the mean. The standard error of the mean, which again comes from this formula, which is represented by this distance, tells you how much each of these increments is. So in this case, we're at a mean of 64 inches. A 95% confidence interval tells us to go 1.96 z-scores, or z-score of 1.96, which means we're going 1.96 standard errors both above and below the mean. And the value of each of those standard errors would be found by doing 2 divided by the square root of 30. And if I take 2 divided by the square root of 30, I get 0.365. So what that means in our picture is each of these increments from here to here is 0.365. And I'm rounding. You could be a little more exact than that. This would also be 0.365. If I want to be 95% accurate, in other words, if I want to encompass 95% of my data, I need to go 1.96 of these increments to the right and 1.96 of these increments to the left. So if I do that, I take 1.96 times the value of each increment, and that's 0.7157. When I say increment, I mean this is the standard error of the mean. This is my z-score, which tells you how many standard errors of the mean to go up and down. So what this is really saying is I want to add 0.7157 to 64. So I want to go to 64, add 0.7157, which is going to put me at 64.7157. And I'm at 1.96 standard errors, so I'd be just a little less than 2 standard errors. I'd be about right there. That's going to encompass this part of the data. Then I'm going to take 64 minus 0.7157. If I do that, I get 63.284. That's going to be taking me 1.96 standard errors left. Encompass this area. 63.284. So again, what I'm doing is I'm going to the mean, I'm going this many standard errors to the right, this many standard errors to the left, and then I multiply by the value of the standard error. In the end, what that means is that I think my population mean is going to be somewhere between 63.284 and 64.7157. If we round, as what our textbook says, that if we're given numbers that are to the nearest whole number here, then we would round this to the nearest whole number. So I'm estimating that our population mean is somewhere between 63 inches and 65 inches if I round that to the nearest whole number. This is called inferential statistics. I'm using sample data to make an inference or an educated guess about my population mean. Now, if I wanted to, well, I guess I should point out that what this does, it gives a 95% confidence interval is giving me 95% of the area of this distribution. Now, you should also understand that you might go out and survey another 30 people. You might get a little bit different sample mean, which is going to change your interval. Okay? A 95% confidence interval means if that 95% of the time, if you go out and sample 30 people, the population mean will actually fall in your interval, which means 5% it won't. So you have to be aware of that if you want to be more sure of your results, you might want to use something like a 99% confidence interval. Of course, right now, this is 95% of the area, 0.95. If you do a 99% confidence interval, you're going to include more of the area, which means your interval is going to be wider. This number would be bigger, this number would be smaller, because you want to encompass more area. So that's my explanation of confidence interval for the mean.